So in this short video, I'm going to attempt to demystify the idea of a non-parametric test and try to just make it a bit more accessible and something that possibly that you might try and use during your research projects. So non-parametric generally strikes fear into people, and it does have the challenge that it can be difficult to define, but we can make a kind of very crude working definition of it without invoking any of the mathematics underpinning it, in that it does not care about the type of distributions that you have. So as you know from the distribution video, we have distributions such as normal, we have binomial, Poisson, log normal, and so on. So there's a variety of different distributions that you can have. And Gaussian or normal distribution is the one that you're most familiar with, particularly from a laboratory setting, when you're doing test quality assurance, for example. But when you're doing parametric tests, which are the things like t-tests and so on, you have to have data that has a normal distribution for those to work. If you don't have a normal distribution, unfortunately, they really should not be used because they're not appropriate for the data you've got. And both parametric and non-parametric tests, they do make assumptions. And those assumptions have to be satisfied for you to actually be able to use that test to analyze your data. So parametric tests, as I mentioned, make the assumption of normal distribution. In non-parametric tests, they kind of don't care. Your data can be anything from a distribution point of view. From a type of measurement point of view that you have, parametric tests generally assume that you have interval data. So what that basically means is that you have data that makes sense, in that a difference between 1 and 2 millimoles is the same as between 2 and 3. So that interval is consistent. Whereas in non-parametric tests, they can handle that, but they can also have ordinal or nominal or any kind of pretty much anything really. So ordinal is something like BMI, where there's a meaning to the order of the data, and nominal is where it might just be blood group or hair color or handedness, like left and right hand. It doesn't matter so much what the order is, because there isn't any order. There just is a list of that particular characteristic. For parametrics, really you're looking at a sample size of 30 is a kind of rule of thumb that people will apply. Personally, not completely convinced by it, because to really be sure from a parametric point of view, you have to be able to formally test the shape of the distribution and check that it's normal. And the tests that you use for that often don't work fantastically when you have a number of samples, even when it's in and around 30 or 40 or 50. Okay. However, on the other side of the coin, we have non-parametric tests, and they'll happily work with 10 or 20 or 30 or 3,000 or 300,000, but they'll happily work with small sample sizes. Your observations have to be independent, so that's the kind of classic one. So they both really need independence of observations, which means that the value of one observation doesn't affect the value of the other. So you have two variables you're looking at. One doesn't directly affect the other just by virtue of it changing. In parametric tests, you'd ideally want equal variance in populations. Non-parametrics don't care so much. And in parametric, really, you're looking at means. In non-parametric, rank ordering, frequencies, medians. It's that side of the fence. So that's what you're comparing from a difference point of view. So as we saw in the discussion of sample size and power, we rarely have a large enough sample, and we often have a smaller one than we would like, but we have to deal with it anyway. And that the more we have in our sample size, the greater the likelihood we will get a real result. Okay, And as sample size goes down, we have a higher possibility of a false positive result. And it's those low sample sizes where the non-parametric would often be used. So I mentioned this idea that we need to make sure that it's close enough to be a normal distribution that we can use a parametric test. And I mentioned this idea that we can also formally test for that using a variety of different methods. And if we test for it then, and we determine that our distribution is close enough to normality that we can assume it's normal in the broad sense, then we can use those parametric tests. Those formal tests include things like the Shapiro-Wilks test, the chi-square test for normality, the Kolmogorov-Smirnov test, but all of those tests are limited by they may need a larger number of samples than you have to really be effective in testing for normality. So you have a small number of samples and you're leaning towards non-parametric, but you don't have enough samples to really be sure that you can use parametric or non-parametric or which one is appropriate. So it's a bit of a catch-22. A very quick and dirty way of doing it is to compare the mean and the median. So if the mean and the median are pretty much bang on or within a few percent of one another, it's likely to be normal. It's quick and dirty and it's crude, but it can absolutely work. Another way is to use a QQ plot, a quantile plot, and effectively what you're doing is almost like something like a line of best fit. So you're looking to see if your data actually, your observations that give rise to a particular mean and standard deviation, if they are actually similar enough to a set of predictions of what you would expect based on that mean and standard deviation. And you can do that in a lot of stats programs, and there'll be a video about how to do that in Excel. But past experience and know-how is actually important as well. And that can really kind of give you an idea of if it's likely that that population would be normal. So if you know that, let's say, glucose, for example, should be normally distributed in most populations, and you look at a particular population and you find it normally, you make the assumption that it's normally distributed, even though you don't have enough samples or haven't done a formal test of this. The great advantage of the non-parametric ones is you can basically use them when you don't know anything about the distribution of the thing you're interested in. Okay, so you don't have to test it, there's no assumptions made on it. And the reason that works is if you come back to the median, which is the middle point, okay, the middle sample point of your data set. So if you were looking at average incomes, let's say, and you think about the median as the number, like if you make a big list of them, it's the one that's in the middle. So let's say it's 50k. If you throw in a few billionaires into that, they will be at the very, very high end. So the sample that's ordered in the middle, the median, will shift slightly, but not by very much. Whereas the mean will shift massively because you've added these very high extreme values. So the non-parametric approach is really not as sensitive to those kind of, not outliers, but those extreme values. In a biological context, most things are not, strictly speaking, normally distributed. Now, people will make the data jump through hoops to make it normally distributed, so they will log transform it or use exponentials or reciprocals to transform the data. And you might think that's a bit of a cheat, but mathematically all you're doing is you're applying the same transformation to all of the data. So it's like, 2 plus 2 equals 4, and then you multiply everything by 2. And you 4 plus 4 equals 8. It's the same data that you have. You've just increased the magnitude of it, let's say. So you've sort of normalized it. And that can be done, or you can just use a non-parametric instead. The reason things are highly skewed in biological sciences is that you may have no kind of normal level of something if it's an abnormal marker of a tumor or some other disease, and it may only appear at very high levels. You may have no low levels because it's incompatible with life, and so on. So there is a bit of a misconception about parametric tests. and non-parametric tests that the non-parametric ones are not as powerful as the parametric tests. And parametric tests will only be powerful if all the assumptions are met. And if they're not met, it's the wrong test to use, so it can't be powerful. The evidence would suggest that non-parametric tests probably are as good in most cases when you have enough samples. So they kind of, converge on usefulness and power at a high enough sample size. But the advantage is that non-parametric will work better at low sample size. And I've mentioned this idea that normality is often assumed incorrectly in publications because you've no evidence and no way to figure out if the data is normal or not. That's why I would be an advocate of displaying data in B-swarm plots or using box whisker plots where you can see the spread of the data and make your own judgment about normality, even if the author has not done that formally for you. So to do a quick comparison of the parametric test where we're comparing means versus the non-parametric test where we're comparing medians, you have a paired t-test. So in that case, you would have someone who maybe you're doing a before and after of a treatment or a drug or something like that. And the Wilcoxon rank sum test does that for the non-parametric tests. For an unpaired t-test, that's the Mann-Whitney U-test. So the unpaired is where you have healthy and diseased patients and you're comparing them. That's the classical for unpaired, and that's also classical for Mann-Whitney U-test. If you have more than two groups you're comparing, you're looking at doing a one-way ANOVA, and we'll come back to ANOVAs later on. And the non-parametric equivalent of that is a Kruskal-Wallis test. Now, to do some of the non-parametric equivalents of the more complex stuff, like the ANOVA, you're probably going to have to step outside Excel, or at least bring something into Excel that gives you the facility to do those, because they are difficult to do, by just writing the formulas into Excel yourself. You're used to the correlation coefficient, the Pearson correlation between two variables, whereas the Spearman correlation would be the non-parametric equivalent of that. So as you can see, there are equivalents to pretty much everything that you want to do parametrically in this non-parametric way of thinking. And I'll finish up with an example then where we have two distributions. So let's say the top panel, that one is going to be, let's make the assumption that these guys are the healthy and these guys down at the bottom are the sick people. And if you eyeball it with histograms, it's very clear that you have a difference between these two. Okay, one of them, the one at the top, seems to have a lot of low values that are high, and then it tails off very quickly, so it's very skewed to the left. And the one at the bottom is more spread out, but you'll also notice that the scale, okay, at the bottom you're going from 0 to 50, at the top it's 0 to 200, so you have a lot of extreme values in one, and also a lot of low values. So if we did a t-test to compare these, we assume they're both bell-shaped curves, so Gaussian normal distribution. They're not, but if we don't investigate and we make that assumption, we'll find a significant difference between these two. But it's rubbish. If we do a non-parametric test, so the Wilcoxon test on that instead, we find a difference of, or a p-value of 0.63, which means there's definitely no difference. And looking at the pattern by eye, that makes sense. Doing a histogram is another very, very valuable way to check for normality, because you can look at the shape of the data, and it's good practice to do that. You can do that in Excel very, very easily using the data analysis tool pack, and all, I would say, statistical packages can do this very easily as well. So there is a good resource where you can have a look at in Sussex, and have a look through this website. It's got a lot of good examples and workthroughs of different aspects of this kind of parametric, non-parametric discussion.